We start with the portion of it will get distributed, so water will take much larger amount of time to indicate a rise in temperature. Okay, so now we start with the portion of temperature distribution. Here we'll be talking about the various different factors upon which the temperature varies as we move from one particular region to another, because we you would also have experienced that the temperature is never consistent across the entirety of the region. Temperature varies. So what are the factors? Here we are talking about the horizontal distribution of temperature, that how temperature varies from one portion of the planet to the other portion of the planet. So here, let us take a look into it. So first of all, when we talk about the factors determining the temperature distribution, one of the important factor is the latitudinal position of the place. On which latitude is the region located? Now, why is it and how is it that it ends up determining the temperature? That is because we have already seen earlier yesterday with the help of the torch example as well, that wherever you have vertical rays falling upon the surface, wherever you will have the rays finding a shorter distance and then falling upon a surface, it will end up having a greater impact in terms of the amount of energy provided. So we do know that direct rays of the sun, direct solar insolation, or rather than this, greater solar insolation is received in lower latitudes. And why is that? Because of the angle which is made by the solar rays and the surface. Angle made by the solar rays and the surface. If the angle made is higher, that is, if it is almost perpendicular, there will be greater amount of heat which will be received in the process. So that is where you come across a scenario where basically in the lower latitudes experience a higher temperature. Always. Always the lower latitude in comparison will experience a higher temperature, and the reason behind that is very simple, because when we talk about the lower latitude, the angle made by the solar rays are larger, there is greater amount of solar insolation received, so that ends up indicating a higher temperature. Whereas when we talk about the higher latitude, that is closer to the polar areas, now there the solar rays, whenever they fall, they are on an inclination. So just you can compare it with the energy that in the morning, in the early morning, or in the late afternoons, or during the evening. Right now, for example, right now, if you take a look at the position of the sun, it is almost about to set, right? So there, the angle made by the solar rays is very small, and also the power of the solar insolation is not going to be very, very high. But if you talk about the same solar rays at 1 or 2 in the afternoon, then it will have a much greater heating effect. Why? Because it is falling very directly. So that is why there is a substantial amount of reduction of temperature. So here you will observe that as you move from the region of the lower latitudes to the region of the poles, the temperature can end up reducing, and it can be in the range of -30, -40 degrees Celsius as you move to the region of the poles as well. Now, for any place in general, when you would have opened up the newspaper, if ever, or news headlines in general, you would have observed that there is a kind of a maximum and minimum temperature which is indicated for any particular place. Are we aware about the factor that what is maximum temperature, what is the minimum temperature? when is it that maximum temperature is observed or recorded for any particular region? When we talk about the maximum and minimum temperature, when is it that the maximum temperature is observed? Okay, good. Few of you know. So, maximum temperature for any region which is noted by the weather stations. So, whenever you come across maximum temperature reading, it is basically around 2 p.m., 2 to 3 p.m. in the afternoon, generally. And what about the minimum temperature? Minimum temperature is observed around 4 to 5 a.m. in the morning. So that is what you have as the maximum and the minimum of temperature recorded in any area. Why maximum is recorded at 2 to 3 p.m.? Because that is when after around 3 p.m. or sometimes 3:30 p.m., that is when the cooling action begins. That is when the power of the solar insolation starts reducing as the sun continues its downward motion overall. So that is why throughout the day when it has been heated, the maximum temperature of the air and the ground surface is attained to be somewhere around 2 to 3 p.m. Okay. Now, another factor which contributes to temperature of a place is basically the altitude of the region. Because when we talk about various different areas, all of them will indicate different temperature. And you would also have come across the fact that, for example, when we talk about, let's say, the region of a hill station or a mountain, now, on top of a hill station, always the temperature is something which you experience to be slightly lower. So that is why with greater altitude, the temperature tends to reduce. And why? Because of the phenomena of normal lapse rate. So as per the normal lapse rate, temperature decreases at an average rate of around 6.5 degrees Celsius per kilometer. So that is the rate at which the temperature reduces. So if you move 2 kilometers higher up, the temperature will reduce by around 13 degrees Celsius. Now, here you might also have a question that when we talk about the places with an altitude, the insolation received is high. Then why is it that the temperature is lower? And there the reasoning is very simple. The reasoning that we followed for understanding the lapse rate, that is the same reasoning that we have. So even despite of the fact that at greater altitude, the insolation received is high, the temperature overall is never higher. Why? Because there is lesser retention of heat. Why? Because the density of the particles are lesser, because the density of the particles are going to be maximum at the sea level, and as you move higher up, the density of the particles reduces. So here, very good. So with altitude, the temperature reduces significantly as the density of air is very less. So as a consequence of this, we will have a condition where the retention of heat is also very less. Okay, hence the temperature is reducing. That is why, hence, despite the greater insolation, greater level of insolation, the temperature reduces with height. Okay. And also due to the snow reflecting the most amount of sun rays, so the absorption capacity is lower. Vikram, my dear friend, that will work in cases where we talk about the snow capped peaks, the regions which are covered with snow. But what if you consider, let's say, the Tibetan highlands? Tibetan highlands, many portion of them, even though they are at an altitude of around 5 kilometers above the sea level, many of the areas are not covered by snow in majority of the part of the year. It is only during the winter months that almost every portion is covered with snow, but in summer months it is not covered with snow. So in that case, that factor of albedo doesn't come into place. So that is basically dependent upon the density of air particles. Okay. Insolation is the total amount of solar radiation received in a particular area for any set amount of time. Okay. Now, after this, we come across certain other factors which will also influence the temperature. Let us understand that. And that is, one of the factor is distance from the sea. Now, distance from the sea, what are we talking about here? So, for example, let us consider two of the different regions of the country. Let's suppose a very rough indicative map. So let's suppose like this. Now here, let us consider a place, Mumbai. Let us consider a place, let's say, Delhi. Now, in the region of Mumbai, you will experience that during the summer months, the temperature is around 34-35 degrees Celsius. 30 to 34, somewhere around that range. And then in the winter, it comes around 20 to 25, somewhere around that. It is a different matter that even when the temperature reduces to 20 or 18, people start lighting up bonfires because it is a kind of a fashion, and everybody you will see sitting across bonfires in Mumbai in the month of January. And you will be surprised to find out that the temperature is only around 18 or 19 degrees Celsius. But when you consider it or compare it with Delhi, in Delhi, the summer temperature goes as oppressive as around 48 degrees Celsius, right? As high as 48 degrees Celsius in the outskirts sometimes. And winter months, the temperature will dip to around 2 degrees Celsius or 1 degree Celsius. So in Delhi, you will find a greater variation in temperature between the summer and the winter. Whereas in Mumbai, you will find a kind of a moderate temperature maintained throughout the year. So always understand that the regions which are closer to the sea or which are basically present on the coastline, they will always have a moderate and consistent temperature, whereas the inland areas, they will always experience extremity of temperature. Okay, I will repeat this. The regions which are present closer to the sea or the regions which are present on the coastline, they will always experience a moderate as well as a consistent temperature, whereas throughout the year, whereas in the case of the inland areas, they will experience extremity of temperature. Why? Let us talk about that. So here, regions. Yes, Yuvraj, very good. Sayyad, very nice. Vishnu, you are also correct. Regions closer to the coastline always experience a moderate and consistent temperature. Whereas regions in the interior in the interior experience extremity. Extreme temperature variations. Why is it so? So let's talk about the why of it. First, when we talk about the coastal areas or the regions across the coastline, that is where on a daily basis you have movement of winds from land to sea, which we refer to as a land breeze, and you have movement of wind from sea to land, what is referred to as a sea breeze. So on a daily basis you will have the movement of land and sea breeze, so that will not allow the place to get extremely heated up or extremely cooled down. This is what is referred to as the marine influence on climate and marine influence. So, all of you who, whenever I talk about marine influence, I always get a couple of candidates. A couple of them might be living across the banks of Brahmaputra or Ganga, and they give the example that, sir, from my area, it always appears as if River Ganga is like a sea or River Brahmaputra is like a sea. It is not at all similar. Always you will have the land and the sea breeze, which will end up influencing the temperature. It will never allow the temperature to be extreme. Imagine if there would only have been wind coming from sea to the land. Imagine if that would have been the condition, always the wind coming from sea to the land. So if the sea would have been warmer, the land would also have gotten warmer. But continuously on a daily basis, you have a reversal of wind there. So that is why neither does the place get heated up significantly, nor does the place get cooled down significantly. Now, what is another reason? The other reason is that coastal areas, what will be the amount of water vapor in the air in the region of the coastal areas? Will the amount of water vapor be high or will the amount of water vapor be low? Very good, significantly high, very, very high. Now, what did we talk about in terms of the retention of heat capacity of water vapor? We talked about the fact that water vapor is able to retain heat for a longer period of time and significant amount of heat is retained. So, because of that high presence of moisture of water vapor, they are able to retain heat. They are able to have a consistency in temperature range. Okay. So, here, these are the two factors basically. So, if you take a look at the two factors, the first factor is consistent motion of land and sea breeze. We'll understand land and sea breeze in the next module when we expose ourselves to the aspect of pressure and wind movement. And then greater amount of moisture in coastal areas means a greater retention of heat. And hence a consistent temperature. Okay. Now, the other factor which will influence the temperature of a region is the prevalent or the presence of the winds, the prevailing winds here. Now, when we talk about the prevailing winds, it basically prevailing means what? Something which is in existence, the existent wind types that you have. So, the existent wind types basically you can have in a particular area a colder wind which blows. In a particular area, you might have the condition where the warm wind blows. So, that will influence the temperature. For example, in many of the cases or in certain years for the past decade, you will observe that the region of North America it oftentimes in the winter months gets influenced by what is referred to as a polar vortex, where you have cold polar winds which start moving through the region of North America, where the temperature dips to -10, -5, and easily below 0 degrees Celsius. Everything almost freezes. So normally, no other region of United States does not experience that particular temperature. But it is only because of those cold winds that the temperature dips quite significantly. Similarly, in the case of the northern part of India, you will experience the movement of a very hot and warm and dry wind during the afternoons in the summer season. And that is what we refer to as Lu. So that Lu, when it blows, it will significantly increase the temperature. So here we talk about the presence of or the influence of the process of advection. So here temperature is influenced by advection. And we have seen the types of advection. Cold advection will reduce the temperature. Cold advection and warm advection. This will lower the temperature, whereas this will increase the temperature. Generally, when we talk about the prevailing winds, we talk about the permanent wind systems. For example, you have the trade winds, westerlies, polar easterlies, etc., that we have not yet covered till now. But this is to give you an idea that any kind of wind pattern can have the potential to influence the temperature of that region. Any kind of wind pattern, you would have experienced this, or I don't know if you have paid attention to that portion of news headlines where you would have heard that if there is a significant amount of snowfall in the region of Jammu Kashmir, in the region of Himachal and Uttarakhand, now the expected weather metric is going to be that it is going to be very cold in the region of Delhi, Haryana, Punjab, and Western UP as well, because the cold winds will start coming down the hills. So that is where it is the advection of or the process of advection which will influence the temperature of that area. Okay. Now, then we have the influence of ocean currents. Again, before we start to panic, ocean currents is something we will study in very significant detail in the portion of oceanography. But what do we understand by ocean currents? So, in the case of the oceans, generally, all of you would have seen a river moving, how a river moves in a kind of a fixed pattern, in a kind of a fixed direction. There is a consistency of flow. Now, when you take a look at the ocean, even though everything appears to be very calm and still, but even in the oceans, you have a consistent motion of water, and you have a set motion of water in a particular direction where you can have, and that moves with a significant amount of speed. It is not as if the water is slowly and steadily moving, it moves with a significant amount of speed, substantial speed is observed. So there, in the oceans also, you will have the presence or the movement of water from one region to another. This is just like the case of the winds. These ocean currents are also very important in order to distribute heat in various different areas. So basically, you have the presence of either warm ocean currents or cold ocean currents. Warm ocean currents which are higher than the average temperature in the surrounding region, cold ocean currents which are lower than the surrounding water temperature. So if any area is frequented by a warm ocean current, it will lead to a rise of temperature. If any area is frequented by a cold ocean current, it will lead to a significant reduction in temperature. Okay. So ocean currents are basically the streams of water that flow constantly on the ocean surface in definite direction, and that is what we refer to as. Okay. The voice of faculty is coming like a robot. Maybe I have graduated to that level where the voice is coming like a robot. Or is it a technical issue or is it something else? It's fine. Maybe Chat GPT has taken over the voice in this case. Voice is fine? Okay. So kindly withstand the robotic voice for all of all the others. It is something that that is a very nice attribute that I would like to gain sometime in my life. Okay. So that is basically ocean current. Ocean current is, what is ocean current? Ocean current is when you have a definite direction of motion. So I understand we have not studied anything about the ocean. I understand we have not been introduced to what is ocean current and why the oceanic waters will move. For a brief moment, don't get bothered by that. Just take a look at this image. Here you will observe certain arrows to be indicated. Now, all these arrows that you will observe, they indicate a definite direction that the oceanic waters they will undertake and a definite movement that they do undertake. So the red arrows that you see, these are your warm ocean currents, which are warmer than normal and warmer than the surrounding water. And the blue arrows that you see, these are the cold ocean currents, which are colder than the surrounding water. So wherever you have, it is just like how you have advection in the case of the winds, these play a similar role in the case of the oceanic waters as well. So wherever you have the presence of warm ocean current, the temperature will increase. Wherever you have a cold ocean current, the temperature reduces. Okay. So cold ocean currents reduces temperature. How and where? Let us talk about that with the help of examples. Increases. Water flows on ocean surface means waves. No, my dear friend. Waves are very different. In the case of the waves, water does not move forward. Water keeps on moving in the same region. When we say ocean current, so imagine that, let's suppose we have the ocean water. So almost around, let's say 20, 30 meters of depth of water for a wide area that is in a consistent motion. These are like rivers of movement in the case of the oceans. That is what happens. So what is the impact of it? For example, now let us take the case of higher latitudes. Higher latitudes means lower temperature. Now if I ask you that in the region of Kola Peninsula, I hope we have marked the region of Kola Peninsula. I had given you in the portion of the map pointing to mark Kola Peninsula. I hope we have seen where Kola Peninsula is. It is for these conditions that I had and these discussions that I had told you to mark it up. So let's suppose in the Kola Peninsula, if I ask you, at these high latitudes, the temperature would be low or temperature would be high. What do you think? Because we are very, very close to pole, somewhere around 70 degrees, the temperature would be very low. In general, the water in many of these areas, they get frozen. But here at these latitudes, but here the water remains ice free through the year. Why? That is because you have the warm ocean currents in the form of the North Atlantic drift. And that warm North Atlantic drift, it warms up the water surface in this area. That is why here you have a ideally very strategic port at the time of the Soviet Union, that is the port of Murmansk. And Murmansk used to basically house the significant nuclear submarine arm of the Soviet armed forces. Now, Murmansk port would remain ice free throughout the year, whereas the other ports at similar latitudes would get frozen in the northern portion of Russia. The region that Murmansk would remain ice free would be because of the presence of the warm ocean current. Okay, so that warm ocean current is quite significantly helpful in raising the temperature of a place. Then another case example that you will have is, for example, here you have the presence of a cold ocean current. A cold ocean current in this region, which is named as Labrador current. Now, while Labrador current sometimes mixes and significantly mixes with the Gulf Stream, some amount of that cold water enters here. in the coastal areas of United States. And that is where the temperature suddenly dips, what is also referred to as the phenomena of a cold wall, where in United States, in the coastal areas, suddenly it becomes very, very cold. Despite the fact that there is warmer waters present in the form of Gulf Stream, people say it is a cold wall which has taken over. The temperature starts dipping quite significantly because of the presence of cold ocean currents. So that is how you have the example of the influence of ocean currents. So that is also a significant, that also has got a significant role to play in influencing the temperature. Okay. Yes, Kambapati, that is correct. And water of Labrador current is less saline. Why? Why do you think that is the case, Somo? What factor affects the temperature of the ocean current? We'll come talk about it in oceanography. And is it have any effect on temperature? Obviously, my dear friend. Okay, you are talking about ITCZ. ITCZ we'll talk about later. How to differentiate it's a cold ocean current or a warm ocean current? We'll talk about that. Why the ocean currents occur? We'll talk about all of them. Don't worry. So now we talk about the isotherms. In the case of ocean current, just understand whenever any region gets exposed to cold ocean current, the temperature will reduce. Any region, when it is exposed to warm ocean current, the temperature will increase. As simple as that. Just like you have cold winds will reduce the temperature, warm winds will increase the temperature. Similar influence will be expected here as well. Okay. Now we come to the portion of isotherms. What is meant by isotherms? So if let's suppose you are tasked with recording the or maintaining a record of temperature distribution in various different areas. Now, how do you record that or how do you maintain that record? Will you end up marking each and every place and maintaining a temperature in the bracket nearby? No. So temperature distribution is expressed with the help of isotherms. What are isotherms? Isotherms are the imaginary lines which end up joining places indicating equal temperature. Iso means similar, therm means temperature. So iso refers to something which is similar, means similar or equal. Therm here indicates temperature. So isotherms will always end up joining those places having same temperature. So for example, here let's suppose I have A. Let's suppose A is experiencing 30 degrees Celsius. B. Let's suppose B is also experiencing 30 degrees Celsius. C. 30 degrees Celsius. D. 32 degrees Celsius. E. 30 degrees Celsius. Right? So the isotherm which will be formed here will be joining the places, all of them, that are indicating the equal temperature. So this is what is going to be an isotherm. This will also be referred to as a 30 degrees Celsius isotherm because it is joining places, all the places indicating 30 degrees Celsius. Hence, it will be referred to as a 30 degree C isotherm as well. Now, can we say that any place lying on this isotherm, will indicate 30 degrees Celsius? I hope that can be indicated, right? Fair enough. So, any place lying on the isotherm shall have a temperature of 30 degrees Celsius. Now, if I ask you a question, that here basically when we talk about the isotherms, can the isotherms crisscross each other? Can that happen where the isotherms will crisscross each other? What do you think? Can we have a condition where we have an isotherm like this and another isotherm like this? Can we have that? Very good. Few of you have said yes. So, and you have said yes with quite a good amount of vehemence and surety. So it is not as if, or the isotherms can never crisscross each other. Why? The reason is very simple and straightforward. So let's suppose this is the first isotherm. Let's suppose this is a 25 degrees Celsius isotherm. And let's suppose this is a 29 degrees Celsius isotherm. Let's suppose. Now, if I consider any of this isotherm, or let me use different coloration so that it is clearer. Let me use a different color here. The 25-degree isotherm is green and the 29-degree C isotherm is yellow. So any place which is lying on this green isotherm will always indicate 25 degrees Celsius. That is why that isotherm is drawn. Here also 25 degrees Celsius. Similarly, any place on this yellow one will always represent 29 degrees Celsius, be it here or here. Now, what about this particular place? Let's consider O. Now, in this place, what will be the temperature? Will it be 25 or will it be 29? The same place cannot have two different temperature conditions, can it? So that is why you will never have the condition where the isotherms can crisscross each other. So isotherms will never crisscross each other. Okay? Now, here the horizontal or latitudinal distribution of temperature is indicated with the help of the isotherm. Now, let us try to study this isotherm. And with this map, I also want to indicate to you that how from the particular portion or a particular map, always you can extract much greater amount of information than what is always apparent. Let us see. So this is basically the isothermic representation or isothermal representation of the global distribution of temperature for the month of January. January is winter in the northern hemisphere and summer in the southern hemisphere. Let me write it down. Winter in northern hemisphere and summer in southern hemisphere. Now here, when we take a look at it, basically, look at these individual isotherms. How can we know the month? It is based upon the monthly data which is recorded. That is when we draw the isotherm. It is not as if suddenly the isotherms will appear because these are imaginary lines, my dear friend. So only after you have recorded the temperature distribution of all the various different places, then you draw the relevant isotherms. Sommelier, they can't intersect because then at the point, two different volume and pressure of gas will be the same. Simple aspect, Sommelier, at the same place, you cannot have two temperature, different temperature at the same point of time. As simple as that. Okay. So can a country divide in both northern part and southern part? Can a country divide in both northern and southern part? Then what happened? That question is not very clear, but I understand it is a very um, heavy question that you're trying to ask. Are you trying to ask that if a country exists both in the northern and southern part of equator, then what will happen? Is that a question that you're trying to ask, Gurjeet? Is that the question? Okay. So, my dear friend, I understand the tenacity of the question, to put it very mildly. But understand, if a particular country is here, it will not be experiencing distinct summer or winter. It will be experiencing a consistency of temperature, that is the equatorial climate. And that is where every day you have the similar temperature. So you don't have a particular country which expands from here to here. So that is why you never come across that particular condition. Okay. So here, when we talk about the January isotherm, observe here, first of all, the northern hemisphere. This is the 20 degree C isotherm, means every point on this isotherm will have 20 degrees. This is a 10 degree C isotherm. As you move in the higher latitude, the temperature will reduce. This is a 0 degree C isotherm, minus 12.5 degrees C, minus 25 degrees Celsius, and it keeps on reducing. Whereas in the southern hemisphere, notice something. Even though it is summer in the southern hemisphere, here you have 20 degrees C isotherm, here you have 10 degrees C, here you have 0 degrees C. Okay. Now, when you take a look at the 10 degree C and the 0 degree C isotherm, they will appear to be almost parallel to each other. Other than this particular portion, they are almost parallel to each other. Why? Because they move through the oceanic regions. These represent the oceanic areas. The southern hemisphere in general is dominated by water. Northern hemisphere is dominated by land. Now, in the case of the water, we have seen that the rate at which the temperature will change, be it increase or reduction in temperature, that is almost consistent throughout the year, isn't it? In the region, when we talk about the water body, the temperature is almost consistent and homogeneous. So it will change very gradually with the latitude itself. So that is why the isotherms in the southern hemisphere, they will be mostly parallel to the latitudes. Whereas when you take a look in the northern hemisphere, you will find all the various forms of twist and turn. Right? Now, it is the winter season in the northern hemisphere. Let us understand that how, when we talked about the concept that water gets in the winter, which is warmer, land or water in the winter months? Which is warmer? Land or water? Very good. Water is warmer during the winter. Let's take the example of that. So for example, let's represent an isotherm, and let's represent a kind of latitude here, any latitude, random latitude. And on this latitude, let us consider a few different places on the same latitude. Let's consider this place A. Let's consider this place B, right? Or if we could have had a slightly different portion, we could have had a greater contrast. So let me try to have a greater contrast here. Okay. Now, let's take this, consider this place as A. Let's consider this place as B. Now, what is going to be the temperature at A based upon the isotherms that you see? The temperature at A is going to be Y0. Temperature at A is going to be minus 12.5 degrees Celsius. Minus 12.5 degrees Celsius. Because it is lying on the isotherm which, or the minus 12.5 degrees Celsius isotherm is passing through that. So the temperature will be minus 12.5. What about the temperature at B? It is 10 degrees Celsius, isn't it? Now, A and B, they are at the same latitude here. But observe the difference in temperature. It is quite significantly large. And which is warmer? Water body is warmer. Why? Because the land has lost heat at a very quick pace. That is why, even if you consider this region, for example, let's consider this region here. Now, this region, let's suppose, or here, any one that you consider. Let's consider D. Let's consider here C. Now, temperature at C will be again minus 12.5, but temperature at D can be as low as minus 25 degrees Celsius. So, in the case of the land areas, it can get very cold, right? Even at these latitudes. Whereas, in order to experience minus 12.5 degrees Celsius over water body, where is it that you need to go? You need to be going somewhere here. In order to experience minus 12.5 degrees Celsius, you need to be moving here. Why? Because water retains heat, and also another factor that we had just now seen, that here you have the warm ocean currents which move. So you hear the ocean is in general warmer. But can we have a certain set of conclusions from here? First conclusion that we can have is that in the southern hemisphere, the isotherms are almost parallel to the latitude. We can have that conclusion, right? In southern hemisphere, isotherms are parallel to the latitudes. Why? Because the southern hemisphere is dominated by water, whereas in the northern hemisphere you have a variation. Can we say that during the winter months, if you draw the isotherm, whenever you come across the water body, the isotherm moves polewards? Because in all these isotherms, you will observe that as soon as they come over the water body, they move polewards. They have a bend polewards. Why? Because the water is warmer. So, in order to experience the similar temperature over land, you need to go much higher up in the case of the water body, isn't it? So, that will be your second conclusion. In winter, isotherms bend polewards. As one moves over the water body. Okay, we can have that, right? So, what about in summer? Summer, you will have the opposite. Let us understand that with the help of a thermal image. So, this is your thermal image representing the temperature during the month of January. This is the thermal image representing temperature of different areas of the planet. So, here you will observe, look how the land areas are going to be significantly colder. The land areas, they are going to be significantly very, very cold. Whereas at the same latitude, the water bodies are going to be very, very warm, isn't it? And here also observe in the southern hemisphere that the rate at which the temperature is changing is very consistent. There is a kind of a parallel condition with which the temperature keeps on changing. Okay. But what about when we talk about, let's say, the conditions during, okay, you need a previous slide. Take the previous slide here. If every point on the isotherm will have the same temperature, some countries at isotherm experience night. So it is not as if this isotherm, this is an average isotherm condition taken on January. So it is not as if the isotherm, once it is been drawn, then it is fixed there permanently. If the temperature changes, the isotherms will also change, isn't it? Okay, I hope that is understood. Now we come to the month of July. That is when you have the summer in the northern hemisphere and winter in the southern hemisphere. Now, in this case, observe the variation in the heat. So you will observe that the land areas, they are significantly warmer. Observe the warmer areas. Land areas will be significantly warmer, whereas the water bodies, they are colder, isn't it? So if I have to draw an isotherm during these months, it will very much dip. While we are talking about the region of the oceans, very much it will dip ever so slightly, because the temperature will be higher as compared to the temperature here, isn't it? If I have temperature, this I consider temperature at A. If I consider this as temperature at B, so temperature at A will always be higher than temperature at B, right? So in this case, we can say that in summer, the isotherms bend towards equator in when crossing over a water body. Why? As water is cooler. In southern hemisphere, the lowest temperature is 0 degree Celsius, not minus. Where did you get that conclusion, Lakshmi? I hope we are seeing the same image here. Look at the temperature in southern hemisphere here. The temperature is in the range of minus 50 degrees Celsius and low. So where are you getting that conclusion? Why it is not a straight line? Why will it be a straight line, my dear friend? Why will the isotherms be a straight line? I hope you understand what isotherms are. Isotherms are not basically your latitudes. Isotherms are not latitudes. So any particular place will have various different conditions due to which the temperature will vary: altitude, ocean currents, prevailing winds, distance from the sea. There will be various different factors. So in any particular latitude, there will be different temperature. For example, even if you consider a region like India, do you think that the temperature, or any particular place, do you think the temperature that you observe in Chennai, for example, the same temperature you observe in the middle of Karnataka as well? No, Chennai is much more oppressive. If you compare the temperature of Bangalore with the surrounding areas, why is Bangalore significantly cooler? Because of the presence of wind pattern, etc., isn't it? So that is why at the same latitude also, you can always have different temperature conditions. That is why the isotherms will never be straight unless and until you are in the southern hemisphere, which is dominated by water. Overall, there is nothing but water. So the temperature will remain consistent. But in the northern hemisphere, when you have so much amount of land, influence of the land will be quite apparent and quite significant. Okay. Now, now we come to the portion which we refer to as the temperature inversion. Now, what do we understand by temperature inversion? So, when we say inversion of temperature, it is basically the presence of certain conditions due to which, closest to the surface, we do not experience a positive lapse rate, but rather than that, we end up experiencing a negative lapse rate. That is what is referred to as temperature inversion. So if you have to write about temperature inversion, the reversal of the normal behavior of temperature in the troposphere, that is what is referred to as temperature inversion. It is quite common but happens for a short duration because of various climatic factors and because of certain conditions that we will take a look at. An ideal situation for inversion is still air, long winter nights, etc. We'll take a look into it. Okay. So, depends on variations in climatic conditions. But first of all, let us understand this a bit better before we go into the types of temperature inversion. You have various different types of temperature inversion depending upon why and how that inversion has happened. But before all of that, let us try to understand what this temperature inversion is. So, under normal conditions, we do know that in the region of troposphere, we have got a positive lapse rate. We have a positive lapse rate. So, when we have a positive lapse rate, what does that encompass or what does that mean? That means as you move higher up, the temperature tends to reduce, isn't it? Colder air is higher, warmer air is below. That is what is positive lapse rate. Now, when the warmer air is at a lower height, colder air is at a greater height. Warmer air will always have a tendency to rise up. Colder air will always have a tendency to sink down. Why? Because warm air is lighter, cold air is heavier. So, whenever you have positive lapse rate, you have a significant vertical motion of air or wind. We have studied that. So, warm air is always going to be lighter because the particles have a greater amount of energy, so they will escape the system. So, warm air will always be lighter. So, it will always rise up, just like the convection current. And then the cold air will always be heavier, it will try to sink down. So, under the positive lapse rate, if I tell you there will be a vertical mixing of air, will that be correct or incorrect? What do you think? Perfect? No doubt in that? It will be correct. So, under the normal conditions, normal conditions mean the conditions that you and I experience on a daily basis. So, that is where you have a positive lapse rate. That means vertical mixing of air. Isn't it? When you have a vertical mixing, means what is vertical mixing? Means the warm air will rise up or air from this region, the lower region, that will try to rise up, air from upper region will try to sink down. So there will always be a mixing. So even the pollutants, etc., they get dissipated. Now this condition is what is also referred to as unstable air mass or simply unstable air or instability of air. Right? Unstable conditions. Now, when we talk about the temperature inversion, due to certain conditions, you have the temperature inversion. Temperature inversion means you have the condition of a negative lapse rate. That means as you move higher up, the temperature will increase. So, in this case, warm air is above the region of the colder air. Now, warm air tends to rise up, cold air tends to sink down. Here, but the warm air is already above and cold air is already below, right? So, in this case, will there be a kind of a mixing of air which will be attained? No, there will be no mixing. So, this is where we have the condition of inversion, that is negative lapse rate. Why this happens only in polar regions? My dear friend, who told you that this happens only in polar regions? Who told you? Where are you getting this information that this will happen only in polar regions? I have not told this. So wait for some time. We'll talk about it. So here, negative lapse rate means no vertical mixing or motion of air. This is when we talk about a stable air. Now, when you have the air which is stable, in that condition, what will happen? There is no vertical mixing. So let's suppose there are a lot of pollutants which have been produced here. A lot of pollutants. Now, in the earlier days, the pollutants would get distributed and dissipated because as the warm air would rise up, the pollutants would also rise up. But here, there is no mixing. So what about the pollutants? They will stay in the same region for a longer period of time. And that is where the regions they experience very devastating conditions of pollution, something that we experience in the northern part of the country. In the northern part of the country, that is why during the winter months, we have very significantly debilitating impact of pollution, isn't it? So that is basically what is referred to as temperature inversion. Why it happens, we have not covered it till yet. We will cover it, that why this happens, why this condition happens where the warm air is above and cold air is below. When does it happen, or why does it happen? So just before that, let me tell you that this temperature inversion can happen because of variations in climatic conditions at various different latitudes. You have various ways in which this particular phenomena of warm air on top and cold air at the bottom can be achieved. So depending upon the ways in which that warm air on top and cold air at bottom or a negative lapse rate can be achieved, that is the category or the criteria based upon the classification of temperature inversion. So you have various different types. That is surface inversion. Then you have what is referred to as subsidence inversion. Then you have frontal inversion. Then you have valley inversion. You also have a categorization of a permanent mechanical inversion, a kind of a transient mechanical inversion. But these are the four kinds that you should be aware of. So, what are these and how do we have this particular kind of condition? Let us try to understand that. Then we will be able to understand and appreciate what this inversion is. How does this happen? How does this take place? So, first of all, we talk about the surface inversion. Okay. Now, when we say surface inversion, it is basically something to do with the surface, some or the other property to do with the surface, and the conditions attained at the surface, isn't it? So, this is basically observed in the region where the surface becomes very cold suddenly. And when will that happen? When the surface loses heat continuously, that is when the surface will become very cold suddenly. And when does that happen? During the winter months. When during the winter months? During the nights. Because in the winter, the nights are longer. And it is during the nights where the surface loses heat, be it summer or winter. The surface will lose heat during the night. The surface will gain heat during the day. So during the night, when they will be losing heat, that is when they will start to become very, very cold. They will lose lot of temperature. So let us understand how this happens. So this is generally observed when the surface loses, suddenly loses lot of heat and becomes very cold. So whenever this happens, that the surface loses lot of heat and becomes very cold, in this condition, now we have seen that for any surface, whatever might be the temperature of the surface, air above it, will it get influenced by the surface temperature or will it be independent of the surface temperature? What do you think? Will it be influenced by the surface temperature or will it not be influenced? It will be influenced by the process of conduction. So this cools down the air above it immediately. Now, here, when we talk about the property of air, air in general, does it transmit heat very efficiently or is it considered to be as an insulator of heat? The basic property of air. When we talk about air, is it considered to be a conductor of heat that it transmits heat very easily or does it stop heat from moving? Okay. So many of you are absolutely incorrect here. Air does not allow an easy transfer of heat. Unless and until the air starts to move, air does not transmit heat easily. Air is considered to be a very good insulator. Why? That is why all the jackets that you wear, all the thermal jackets, whenever you go for trekking in the mountains, or whenever you go to, let's say, in the winter months, you go to Ladakh, etc., whenever you have the or the cold weather jackets that you have, you'll find that it has got a lot of air trapped in between. It is very fluffy, isn't it? Why do you think there is that much amount of air trapped into it? Because that air does not allow your body heat to escape outside. It retains the heat. Air is always a very, very bad conductor of heat. It is a perfect insulator of heat. That is why air and the winter clothing, any winter clothing that you will see, the basic purpose of how it provides you warmth is not because of the property of wool. It is because whether a particular fabric is able to trap air between them or not. Okay, I hope that is understood, because this is one of the many of you I'm sure would have got a kind of a eureka moment as of now. So air is a very bad conductor of heat. It is a insulator of heat. So why have I talked about that? So that means if the air here is colder, will the air also present here, will it also become naturally very cold? Or will that transfer of heat not happen efficiently? It will not happen efficiently because air is an insulator. So, with that, let us understand the basic concept of surface inversion. Let us consider the ground surface. And that is during the winter. Now, let's consider a place. Let's suppose we consider a region such as Ludhiana or Chandigarh, Ambala, or Delhi, any of the place where actually you experience the winter. Now, here, when we talk about, let's suppose we consider two different conditions. One is at 4 p.m., another one we will consider at 3 a.m. Now at 4 p.m., if suppose the ground temperature, let's suppose the ground temperature is 10 degrees Celsius. Okay, that is your ground temperature. And try to apply your logic here, guys. Don't simply look at what is being written. Apply your logic if it satisfies your logic. Now, if the ground temperature is 10 degrees Celsius, the temperature of the air immediately above the ground will also be very similar. Let's assume 10 degrees Celsius because it is in contact with the ground. The air in contact with the ground. Air in contact. Now, as you move slightly further higher up, there will be lapse rate, moist lapse rate, dry lapse rate. Let's not get into that entanglement. Let's assume that as you move slightly higher up, we do know that the temperature will reduce. Let's assume the temperature has reduced to around 5 degrees Celsius. As you move further higher up, let's suppose the temperature has reduced to 0 degrees Celsius. This is at 4 p.m. Till here, are we comfortable till here? Right? Perfect. What is the issue, Roshan? Till here, I hope we are comfortable. Good. Now, here, during the night, that is 3 a.m. in the morning. Now, the sun will set around 5 p.m. during the winter months. And you would have observed during the winter months, it starts getting colder immediately afterwards as the sun sets because the ground continues to lose heat, isn't it? So, here at 3 a.m., let's suppose the ground temperature becomes 2 degrees Celsius or 1 degree, because in the region of Ludhiana, Kapurthala, Jalandhar, in that entire area, the temperature at night sometimes can get even up till around zero point 0.5 or 1 degree or 0 degree Celsius also is attained. So let's assume that you have the temperature at 2 degrees Celsius of the ground. Now, what will be the temperature of air immediately in contact with it? The temperature of air in contact, or let's assume rather than 2 degrees Celsius, let's assume 1 degree Celsius or 0.5. So here also air in contact will be 1 degree Celsius. That will also indicate 1 degree Celsius. Here at this particular height, the temperature would reduce. But would it reduce at the same drastic rate as you observe on the ground? No, it will not reduce at the same rate because it is not in contact with the ground. And air is an insulator. Air does not lead to a transfer of heat or coldness. So here, let's assume the temperature has reduced at this height also, but it has reduced to around 2 degrees Celsius or 2.5 degrees Celsius. Here also it has reduced, let's suppose at this particular height, here also temperature has reduced to around, let's assume, minus 2 degrees Celsius. But in these conditions, what will you observe? The air at the ground surface has cooled down at a much more drastic rate. Why? Because the ground surface has lost heat. During the night, the ground surface has become very, very cold. And because of that, the air in contact will also become very, very cold. So what do you have? Here, in comparison to the ground, you will have warmer air. Here in contact, you will have cooler air. So cooler air at the bottom, warmer air at top. What is that? Isn't that a negative lapse rate? Right? So that is basically the condition of temperature inversion. That is what we have as the temperature inversion. This is your negative lapse rate. It can even be 3 degrees Celsius, 1.5 degrees Celsius at this level. Anything can happen. But It is a negative lapse rate. Now, why has that negative lapse rate been attained? It is purely because the ground has lost heat at a very quick pace. If the ground would have not cooled down so significantly, the air in contact with the ground would also not have cooled so significantly. So this temperature inversion which is attained, that is basically what is referred to as a surface inversion, because it has been attained purely because of the cooling of the ground surface, the sudden cooling of ground surface. Okay, how many of us are very confused about this 2.5 degrees Celsius and 5 degrees Celsius? How many of us are very confused at how this number 2.5 or 5 or 0, what is he talking about? Okay. What if I were to tell you that this is an assumption of temperature that we have? Can we have that, an assumption of temperature? There is no calculation involved in this. If I tell you, will that satisfy your query? Or are you still confused? Why only 5 degrees Celsius? What is the meaning of not sure? Okay. Why does air at a greater height lose heat? Because during night time, in general, there will be cooling, isn't it? This is still very much in stratosphere that we are talking about. We are troposphere. We are talking about, Chandrasekhar. We have not even. Why will we be concerned with stratosphere? This is not at all about stratosphere. Okay. It is an assumption. The temperature that you see 5 degrees, 0 degree, it is an assumption, simple assumption. Okay. Why 5 degree? Because do we know the height between here to here? Have I anywhere have I shown you the height? Let's assume the height is 750 meter. Then what? Will it satisfy the condition of your lapse rate calculation? No? Okay. Can you please repeat this concept again? But 2.5, how? Okay, what if rather than 2.5, I write here 3 degrees Celsius? Then how many of us have a doubt? If I write here 3 degrees Celsius, are we able to understand the basic air? Isn't air a good refractive medium? Uni, how is that relevant here, my dear friend? Chitranshu, where does the ground loses heat? If it loses, so the ground, when it loses heat, that heat escapes higher up. That heat, many of the time, is lost to the space as well. Okay. Terrestrial radiation by land heat up air above. No, no. Terrestrial radiation by land, why will it heat the air above? That terrestrial radiation is lost. If that would have been the case, then during night time, the air would have been very hot. During daytime, when air is not losing heat, air would be very cold. During night time, do you experience the air to be cooler or not? Have you experienced the air to be cooler or not during night time? It can easily pass other materials through it. Yes, but the heat is not transferred through air only. Surface inversion and temperature inversion appears to be the same. My dear friend, surface inversion is a kind of temperature inversion. Temperature inversion has got various different types. So temperature inversion has got different types here. You have the surface inversion, subsidence inversion, frontal inversion, valley inversion. There are other kinds of inversion as well. Okay. So here, first of all, do one thing, read the written portion so that you have some amount of digestion which happens. and then I will again repeat the entire concept. Don't worry about it. And then I will take different figures and different numbers for that matter, so that you don't get that kind of uneasiness. A surface inversion occurs, read it carefully. A surface inversion occurs when the atmosphere at the Earth's surface is colder than the layer above it. What is the meaning of this? This means if this is the ground surface, here somehow you will have warm air, and there is a condition due to which here you have a cold air. And this is created due to the mechanism of the surface. Hence the name surface inversion. And again, it is a type of temperature inversion. Now, here, around sunset, the ground cools rapidly by radiating heat upwards into space. Some of that heat is retained by the atmosphere in the upper region, but heat is lost. The air in contact with the ground cools by conduction, causing the lowest layer of the air to be cooler than the higher layers. That is how you attain the condition where the cold air is at the ground, warm air is at the top. Okay, so here when we talk about another aspect, I'll give you another example. So let us understand with the help of another example. So basically, have you just given an example, my dear friend? That is why we considered Ludhiana. Otherwise I would have considered Chennai as well, Trivandrum as well, Goa as well, coastal areas. I considered Ludhiana. Why? Because that is where you experience this. Let me consider the region of Delhi. Surface inversion, winter nights, winter months rather, in Delhi. Now, let us consider the conditions. Let's assume I'll change all the figures now. Okay. So here, let's assume we consider the condition at 5 p.m. and then we consider the condition at 2 a.m. in the morning or 4 a.m. in the morning. Okay. Now, please don't ask me why only 4 a.m. Earlier, I had given you the example of 3 a.m. Now, I'm giving you the example of 4 a.m. You can take the example of 2 a.m. as well, 1 a.m. as well, anytime at night. Okay. Why only 5 p.m.? You can take any other example, whatever you like. You can take the example. So, here, let's assume this is the ground. This is your ground. Now, the temperature at ground during 5 p.m., let's assume is 12.5 degrees Celsius. The problem is when you start using numbers like 10 and 5 and 0, people are very quick to use the calculation of adiabatic or the lapse rate in general. So let's this time use decimal pointers so that you have some amount of difficulty in calculation, so that you understand assumptions. So, okay, I'll write it down. All temperatures are indicative and assumptions. They have no relation with reality. Any relation with reality is purely coincidental. Okay? Just like you have a caveat before the movies. So here, the temperature at the ground surface, let's assume, is 12.5 degrees Celsius. Till now, I hope we are comfortable. Now, the air immediately in contact with the ground surface will also have a temperature of 12.5 degrees Celsius, air immediately above it. So here also temperature is 12.5 degrees Celsius. This indicates air in contact. As you move higher up for a set distance, I'm not telling 1 kilometer, 2 kilometer, 50 kilometers, 100 kilometers, 1 meter, 200 meter. I'm not discussing the distance here. Let's assume you move slightly higher up. Under normal conditions of positive lapse rate, you will experience a reduction in temperature. I hope we are comfortable with that. That as we move higher up, the temperature reduces. By what quantity, where, how much, leave it to the some other heavenly being. So here the temperature will reduce as you move higher up. Let's suppose the temperature here is 6.25 degrees Celsius. Again, an assumption. It is purely an assumption. Okay, it has got nothing to do with the lapse rate that we have calculated. Assumption that it reduces. Okay, yes, 12.5 is an example. All of these are examples. Now, this is your assumed temperature at a height. Now, as you move further higher up, due to normal lapse rate, the temperature will reduce even furthermore. I hope that is understood. Let's assume the temperature is 1.5 degrees Celsius. Let's assume. Are we comfortable up till this point? Any doubts that we have till this point? Any doubts? This is what is positive lapse rate. Perfect. All those who had doubts, ask it now. Not at the end that repeat the entire thing. How 1.5 degrees Celsius? Assume. Assume the temperature will reduce. What is the temperature that you want me to write here? I'll write that temperature. Any temperature that you want, I will write it here, Roshan. Any temperature. You want me to write 0 degrees Celsius? I'll write 0 degrees Celsius. It is just an assumption that as you move higher up, the temperature will reduce. Okay? Is that perfect? Now, when we talk about 4 a.m., basically 4 a.m. means after 5 p.m., generally the sun will set. As the sun sets, there is no gain of heat. There is a consistent loss of heat which is experienced. So, as that heat is being lost consistently, the ground will get colder. Now, please don't get into the conception that when the ground loses heat, the air above it gets heated up. That is not what happens. Please understand, if that would have been the case, then as you would have moved higher up, the air would have gotten warmer. It is not the case that the ground loses heat, so the air will get warm. When the ground loses heat, that terrestrial radiation is not trapped by the troposphere, it escapes. Some of that is trapped in the higher extent of the troposphere, some of that in the higher extent of stratosphere, but majority of it escapes. Okay, so here in the ground, basically, let's have an assumption, let's take an example that the ground surface at 4 a.m. will become very, very cold. So here, if the temperature is 1 degree Celsius, let's assume the temperature is 1 degree Celsius. So the air in contact will be how much? 1 degree Celsius. Perfect. As you move higher up, the temperature will reduce, but will not reduce at the same rate. Here, the temperature will reduce in comparison to the earlier proportion. Let's assume the temperature from 6.25 degrees Celsius has reduced to 3 degrees Celsius. Let's assume temperature has reduced. Temperature has reduced as compared to 5 p.m. Now, this loss of temperature at this height has got nothing to do with the ground here. Why? Because it is not in contact with the ground. So this is independent of the ground temperature. Independent of ground temperature. Now, in this situation, the air at the ground level has a temperature of 1 degree Celsius. The air at a particular XYZ height is 3 degrees Celsius. So this is what? This is an ideal condition which will indicate warmer air above, colder air below. This is negative lapse rate. But why has this negative lapse rate been attained? Because the ground has cooled down quite sufficiently and quite quickly. That is why this negative lapse rate has been attained. This is what is surface inversion. Because the surface has cooled down, that has cooled the air immediately above. That is what is surface inversion. Is that now understood? I hope that is clear now. Okay. What happens in the morning? Does this situation change? Obviously. During the morning, as the ground will get heated up, again, the situation will change. The situation will revert back to normal. Okay? Good. Now, this is your surface inversion. So, under which conditions will you experience the surface inversions? Conditions where you, and I see many of you are not clear with the portion of what is meant by negative lapse rate. So in that case, kindly revise the portion which has been taught yesterday. You will understand negative lapse rate and then understand this. In case even that is not understood, then we can't be repeating the entire thing. So here, when we talk about the conditions required, the conditions are basically winter nights, long winter nights, right? Long winter nights, when you have calm air and still air, that is when the heat will be lost very quickly. Clear sky to enable quick loss of heat. Because if there is cloud cover, clouds will have water vapor. Water vapor will retain heat. It will not allow the heat to be lost. That is why in cloudy nights it is warmer. In cleared skied nights, it is going to be much more colder. So this is a kind of an inversion that we refer to as the surface inversion. Now we have another kind of inversion which is referred to as the upper air or subsidence inversion. Now this is a kind of an inversion which you don't experience in regions such as India. Surface inversion, by the way, in India, where do you experience that? In India, either you will experience this slightly in the hilly areas or in the region or in the northern areas, especially during the winter nights. In the southern part of India, you don't end up experiencing that. Now, then when we talk about the subsidence inversion, subsidence means something is sinking. Now, this is observed in the higher latitudes during the winter months. So, observed in the higher latitudes, in higher latitudes during winter. So what happens here? So basically when you have the winter condition or and that too in higher latitudes, what will be the ground surface temperature? Will it be high? Will it be low? What do you think? Will it be high or will it be low? Why will it be high? Are we, Roshan, do we know the meaning of higher latitudes? What is the meaning of higher latitudes? Higher latitudes basically refers to the region near the poles. Now, the region near the poles during the winter months, will it have higher temperature during the night? Never. It will have very low temperature. So, ground has got very low temperature. Now, why does this inversion happen? Is understand. Now, sometimes, let's suppose if this is the ground surface, sometimes from the upper region of troposphere, when the air becomes very cold, it will start to sink. Air, when it becomes very cold, it becomes heavier and then it will start to sink, right? So, here, when the air begins to sink, it will go into the region where the air density is higher. And when the air sinks and goes into the region where the air density is higher, can we say it will undergo a kind of an adiabatic compression? Can we say that it will go for it will experience an adiabatic compression? Adiabatic compression brings about heating of air or cooling of air. It will bring about a heating or a cooling. Heating of air. So let's assume you have here you have cold air and here you have, let's assume, a colder air which started sinking, air column which started sinking, or any parcel of air, any sample of air which started sinking. This is your sinking air. Now that sinking air, as it goes further lower, it will undergo a kind of an adiabatic compression. Adiabatic compression will provide warmer air. So in case where this temperature of the warmer air is even zero point 0.1 degree Celsius higher than the colder air, don't we have a negative lapse rate? Isn't it? So that is basically the temperature inversion which is created by the subsidence of air, and hence it is referred to as subsidence inversion. So when a widespread layer of air starts descending, it leads to subsidence inversion. The resulting increase in atmospheric pressure, don't bother about the atmospheric pressure, just think about compression and heating is caused due to the adiabatic process. Okay, right? Why will it start sinking in the first place? Because let's assume this air is cold. Cold air is heavier, it will always try to sink, right? So that is why it starts sinking. Okay? Now, let's take a break, and then after the break, we will carry on the study of the various other inversions, and then we will move into the next module. So we take a break, 15 minutes. Inversion because it is already a warmer air above. That is why. Okay. Why will the descending cold air undergo adiabatic compression? Because it is coming into a region where the air density is higher. Air density is lower at higher altitude. It is uh, higher at the lower altitude. So as the air descends, it will get compressed, and that is why heating. Now, this is something which persists for a longer period of time as compared to the surface inversion. In the case of the surface inversion, we have seen that in the next morning you can have the reversal of the condition and the normal conditions can prevail again. But in this case, this can persist for a longer period of time, because here this is controlled by the sinking of air. Now, this can oftentimes and sometimes can lead to very bad conditions as well. I'm sure you would have heard about the case of, or if you have not heard about it, try to explore about the case of London smog. London smog, which happened in 1952. Now, around that period of time, in the early 1950s, now obviously across the region of Europe and across the entirety of the world, fossil fuel combustion would be quite a norm. Burning of fossil fuel, etc., would be quite a significant norm. And people would use burning of coal, etc., in their domestic purposes as well. And there, under these conditions, during the winter months, you had a subsidence inversion which happened, which persisted for a good 14 days or somewhere around that period of time. Now, during that interval and during that period of time, the pollutants persisted or continued to stay in the lower region. All the pollutants, all the greenhouse gases, they continued to stick to the lower regions, and people inhaled that. Many people were hospitalized, hundreds of them. Many people even lost their lives. So that is how this subsidence inversion can actually persist for a longer period of time. Now, then we come across something which is referred to as the frontal inversion. Now, this is observed whenever you have creation of a front. Now, frontal creation or a front creation is something we have not discussed till now. We will talk about it later on, and then again, I will revisit this particular topic. But let us understand, what do we mean by frontal inversion. So here, let's suppose we have a region, especially this is again something not observed in India. This is again something observed in mid latitudes. So here, mid latitudes basically means around 40 to 60 degrees latitude. That is the mid latitude. Now, here from one side, you have the cold polar air, very cold air. And from one side, you have, let's say, the presence of warm air. Warm air will always have a greater amount of volume. Warm air will always have a greater volume, because anything which is hotter will tend to expand ever so slightly. Anything which is cold will have a compressed volume. Now, if suppose there is a movement in any of these cases, if the warm air is moving or a cold air is moving, now generally the perception that we have is that when the air will move, it will readily mix and we have a homogeneous mixture. But that is not the case. If you have a cold air which is spanning for thousands of kilometers in its width, now that cold air will form a very condensed or a compressed volume. And when the warm air comes in, that warm air will immediately start rising up on that cold air like an inclined plane, because the cold air is so heavy and compressed, it will stick to its ground. Cold air cannot be lifted easily. So here, the warm air will start riding upon it. So as it starts to move, that warm air will start to ride up above it. Right? So you have warm air. Now, in any particular section that you observe here, what do you have? You have cold air at the bottom, whereas you have warm air on top. This is what? This is a kind of a negative lapse rate. This is a kind of a temperature inversion. But this inversion has not been caused because the surface has cooled down suddenly, or this inversion has not been caused because the air has subsided and there is an adiabatic compression. This inversion has been created because there are different air parcels which are interacting and overriding one another and each other. So, this is what is referred to as a frontal inversion. Okay. This is what we refer to as a frontal inversion. Then we have what is also referred to as a valley inversion. which is observed in the valleys during the, we have the mountains and valleys. We have studied what valleys are. So these are observed in the valleys during night time. So observed in valleys, during night. Now understand the process behind it. So basically, when we say a valley, let's suppose a mountainous area. Valley in general will be surrounded by hills and mountains on both the sides. Let's suppose these are your mountainous areas. Now, during night time, if I ask you the conditions which will prevail during night time, now the temperature at the top of the mountain, will it be low? Yes or no? Temperature at the top of the mountain during night, will it be low? Significantly? So, considering the night situations. So, if the temperature is low, can we say we will have cold air here? In both these areas, we can say we will have cold air. Okay. Now, if I ask you what will be the temperature in comparison at the valley bottom, will it be perfect to say that the valley bottom in comparison will be warmer? It will be okay to say that the valley bottom in comparison will be warmer as compared to the top of the mountain, right? So here you have warm air. Till here, I hope everything is digested. Now, which is going to be heavier, colder air or warmer air? Which is going to be heavier? Always colder air. So the colder air, when it is heavier, it will be attracted by the gravitational pull here. It will start sinking. And can we say it will replace the lighter warm air? The lighter warm air will be lifted ever so slightly as the cold air replaces it, because the cold air which is sliding down the mountain, that will replace them, isn't it? So the cold air from the mountain top sinks and replaces the warm air at the valley bottom. Now, in this case, what do we have? Again, warm air on top and colder air at the bottom. So that is an inversion. But this inversion has not been caused because of a front. This inversion has not been caused because of subsidence. This inversion has not been caused because sudden cooling of surface. This is an inversion which has been created purely because of a setup of a mountain and a valley. That is why this is what is referred to as a valley inversion. That is the reason why in very narrow and closed valleys, it is never suggested to stay at the valley bottom during the night, because the temperature will get very, very low very suddenly. We are not talking about very large valleys where in the valley bottom you can have various cities, etc. That large valley. No, we are talking about small, narrow valleys. And here, sometimes what happens is that if you have, let's say, mountains, and then there is a kind of a passage through which, and that mountain setup is not closed from all sides. So if you have a kind of an open system of mountains where the air can move in between freely, then the conditions won't get so drastic suddenly. But if you have a closed setup where the air is unable to drain itself significantly, then all that cold air accumulates at the valley bottom. That is why any valley that you come across, from now also, if you start observing any narrow valley that you come across, you will never find habitation or settlements at the valley floor. You will find that the settlements will happen either here, here, or here. Settlements will never be observed at the valley bottom because it gets very, very cold suddenly during the night. Many of the plants, they die because of sudden frosty conditions. This will happen in the case of closed valleys. If the air is allowed to move freely, then in that case, this condition won't be very drastic. Okay. Why warm air at valley bottom? Because we have just now seen that with the altitude, the temperature reduces. We have seen in the case of temperature variation that as you move higher up on top of the mountain, the temperature will be lower. So during the night, you will always have colder air here and warmer air here. So that is why it will happen. So, and by the way, this particular portion, whenever you study in the portion of NCRT, it is mentioned incorrectly. A paragraph is skipped in the NCRT. So, please don't get misled by reading the NCRTs in this particular portion. So, here NCRT is incorrect. So, this will be observed, to be observed in narrow valleys. Okay, where the air doesn't get any scope to move. Okay. NCRT book is very, very good. I agree. But NCRT has got certain mistakes, and it is our job not to get misled by the mistakes. Because once you commit the same mistake in the examination of civil services, you will not have anybody where you can show that NCRT, but in NCRT, this is given. Nobody will bother for that. So that is where you have to be very careful. So that is the case of valley inversion. Okay. Now let us take a look at the prelims questions or the PYQs. Normally, the temperature decreases with the increase in height from the Earth's surface because the atmosphere can be heated upwards only from the Earth's surface. There is more moisture in the upper atmosphere. The air is less dense in the upper atmosphere. What is the answer for this? That normally the temperature value with correct. The atmosphere is heated significantly from the Earth's surface. There is more moisture in the upper atmosphere. This is incorrect. And the air is less dense in the upper atmosphere. That means there is less retention of heat. So the correct answer here will be C. Okay. Now, then another one. The annual range of temperature in the interior of the continent, annual range of temperature means the variation in temperature between the summer and the winter. The annual range of temperature in the interior of the continents is high as compared to the coastal areas. What is or are the reasons for the same? Thermal difference between land and water, variation in altitude between the continents and oceans, presence of strong winds in the interior, heavy rains in the interior as compared to the coastline. Why is it that interior areas have a greater range of temperature throughout the year? For example, if you consider the region of the Central Europe, in many areas it is close to around 50 meters or 100 meters below sea level. So there, this is an incorrect one. That is not responsible for the variation in temperature. So the second one is incorrect. Now, again, these were the good old days of elimination where you could easily eliminate all the areas where 2 has occurred. Presence of strong winds in the interior, incorrect. The winds are very, very strong in the coastal areas. They are not strong in the interior. Heavy rains in the interior as compared to the coast. This is also incorrect. So that is why the correct answer will be A. That is one only. That is because here you will always have a kind of a moderation of temperature in the coastal area, but greater variation in temperature range in the interior areas. But there is cloud formation because of moisture. So how is that relevant? Why fourth is incorrect? Only heavy rains in the interior as compared. Always coastal areas will receive higher amount of rainfall. Any place that you go through, coastal areas will always receive higher amount of rainfall. Okay. Kambapati, adiabatic compression does happen slightly, but not quite significantly. So that adiabatic compression does happen, but then because the temperature is so very low in at the mountain tops and the air at the mountain tops, that even after compression it will be colder than the valley air. Okay, now we come to the portion of why option 2 is wrong in the first question, Trisha. There is more moisture in the upper atmosphere. How can this be correct? Moisture is always to be the found to be the greatest in the lower region, right? And if there would be more moisture in the upper atmosphere, that means it would have been hotter in the upper atmosphere. Okay. So now we come to the portion of the atmospheric circulations. Yes, all these are PYQs. There are a couple of more PYQs which have been asked this year related to this, but we will discuss it in the coming week. Okay. Now, we come to the portion of atmospheric circulations. Now, when we talk about atmospheric circulations, this is a particular unit which is going to be very substantial and very helpful, along with the topic that we just now covered, that is the atmosphere and temperature. So, this is going to lay the foundation. If you understand and if you basically revise this and lay a foundation for this, you will be able to have a much better clue about the aspects as detailed as, let's say, El Nino, La Nina, jet streams, Indian monsoonal systems, all the various complicated concepts that you come across, even cyclonic circulations. It will be much easier to understand if we understand this particular topic. So, for this, the prelims, what are relevant for your prelims here? So, in the prelims, you get questions about basics of permanent winds, sometimes even factors influencing movement, wind movement, then types of local winds, and their regions where they exist. So at the end, now this is something which is very theoretical about the local winds. I'll explain to you about what these local winds are, etc. And at the end of this particular module and the PPT, I will provide, and I have provided in the PPT itself, a compilation of all the various different types of local winds. So that will be something which will be helpful to you. Okay. Now, for the mains examination here, generally the utility of these particular portions are applicable in the complicated questions asked in the mains, where you need to involve multiple different concepts together. But when we talk about the mains exam, here you have the permanent wind system, and also sometimes pressure belts. Okay, that is something relevant for your mains exam. So here, first of all, in this particular portion, we are going to introduce ourselves to the concept of atmospheric pressure. What are the various factors upon which the atmospheric pressure can depend? Then we will be talking about the factors based upon which the wind movement is actually dependent upon. And after that, we shall be understanding the permanent wind systems across the globe. Permanent wind systems means the wind systems which continue to move throughout the year in across the planet. So that is something we'll take a note of. And after that, we shall be introducing ourselves to the concept of local winds. Okay. Now, here, when we talk about atmospheric pressure, what do we understand by pressure? Pressure is basically the total amount of force which is applied per unit area. That is pressure. So, for example, any object for that matter, take any object, if it applies some amount of force, that is something which is regarded as pressure. So, when we talk about pressure and atmospheric pressure in general, we refer to the weight of the entire air column on the ground surface. The air column will consist of the gases, water vapor, as well as the dust particles. So the weight imposed by the air column on the ground surface, that is your atmospheric pressure. So this is your definition of it. So the weight of the column of air contained in a unit area from the top of the atmosphere to the almost sea level, that is your atmospheric pressure. This is expressed in the units which is referred to as millibar, and a normal average air pressure is referred to be around 1013.2 millibar. Now let us understand this. So for example, we consider the Earth's surface or any ground surface. Now above it, you will have the air. Now the air column will consist of various different gaseous molecules. It will consist of various different gaseous molecules. Now, all these gaseous molecules, they will exert a significant amount of weight here. They will end up exerting a significant amount of weight. And that weight which is experienced, that is what is referred to as atmospheric pressure. Now, we have already seen a couple of cases about the aspect of temperature. By the way, pressure is not only dependent on temperature. Majority of us, we have a misconception that pressure is always dependent on temperature, but it is not always so. So understand one of the basic concept. Let's suppose I have two samples of air. Let's suppose I consider any two samples of air. Now, let's assume this has got various different air particles. This is now, if I heat this air up, if I warm it up, what will happen to the molecules? The molecules will gain some amount of energy, and many of these molecules, they might escape that system as it gains energy, isn't it? So let's suppose I warm this air up. So can I say that the molecules will gain a lot of energy? The molecules will escape the system. Can I say that the molecules will get lighter? And when the molecules get, or the air sample in general will get lighter, and when the air sample gets lighter, what will happen? Anything which is light will rise up. So this starts to rise up. Isn't it? Rising air. Now, what will be the impact of pressure? If let's suppose this is the ground, from this air is rising up. What will be the pressure? Pressure is the total weight imposed by the air column. But if the air in itself is rising up, the pressure will increase or will the pressure reduce? What do you think? The pressure will decrease, isn't it? The pressure will decrease. So whenever you have a rising air column, now that rising air column can be initiated due to temperature, can be initiated because of other factor as well. So rising air column will lead to decrease in pressure, or what we also refer to as the condition of low pressure. Conversely, let's suppose here I have the presence of colder air. Now, colder air the particles will get much closer to each other because they have lesser energy. When they have greater energy, they roam around, they move around, but when they have lesser energy, they will stick closer to each other. So that colder air, will it become lighter or heavier? It will become heavier, isn't it? So become when you have cold air, now that cold air becomes heavier, and anything which is heavy will tend to sink. So you have sinking air. Now what will it lead to? On a ground surface, if you already have a sinking air, what will be the impact of pressure on the ground? It will increase the pressure. So always sinking air, always air column will lead to increase in pressure, and that is what is referred to as high pressure. No, the amount of air inside the box does not remain the same. When you cool down the air, more particles will stick together. That is why the colder air is heavier. When you warm the air, many of these particles will escape the system because they have greater energy. So that is why this parcel will become lighter. Okay. So that is the condition of high pressure, and that is the condition of low pressure as well. Now, this is your definition of atmospheric pressure. That is the total weight imposed by the air column on the ground surface from top of the atmosphere. That is what we refer to as atmospheric pressure. Now let us understand a bit more about it. Until now, we will be talking only about temperature as a controlling factor of pressure. However, let me write it down here itself. Pressure is dependent on temperature as well as the movement of air. So, temperature is not the only controlling factor. So, temperature is not the only controlling factor. So, it can happen that in areas which are warm, that can be a high pressure also. So, open your mind to that possibility. We'll talk about that possibility later. So, it can always end up happening. Now, here, let us consider the condition in certain regions. How is it that the air circulation is attained? Let us assume this is the tropopause. Now, air will rise up till what condition? Till when will the air rise up in general? When you have a warm air which rises up, till when will it rise up? As long as it is warmer than the surrounding, as long as it is warmer till that point of time, only it will be lighter than the surrounding, isn't it? So the air will always rise up only as long as it is warmer than the surrounding. I hope that is clear, right? So let me write down that portion as well. So air will rise as long as it is warmer, hence lighter than the surroundings. Okay. The moment that it becomes colder than the surrounding, it will start sinking. The moment it becomes at an equal temperature than the surrounding, it will stay at that level itself. As long as it is warmer, it will continue to rise up, isn't it? Now, here, let us consider the condition here. So let's suppose you have a particular region which is heated by the sun, significantly hot region, hotter area. Let's suppose we consider another one that is colder area. Now, first of all, let us consider the hotter region. Now, in the hotter area, once the ground gets heated up, the air above the ground will also get heated up. When the air above the ground gets heated up, the particles in the air will gain energy. They will start vibrating. Many of them will start escaping. So, any parcel of air that we consider will become lighter. So, in this case, what will happen? Let's suppose you have a parcel of air here. So, it becomes lighter. So, it will start to rise up. It will begin to rise up, isn't it? So, this begins to rise up. So, air gets heated. And rises up. So, it will continue to rise up as long as it is warmer than the surrounding. It rises up, rises up. At max, in majority of the cases, it will be able to rise only up till tropopause. Why? Because beyond tropopause, you have the warm stratosphere. Warm stratosphere. So the surrounding is warmer. So the air in the surrounding, in this case of stratosphere, will be slightly lighter in itself. So that is why this air which has been rising will not reach the level of stratosphere. Now here, once the air hits the ceiling in the form of, let's say, tropopause, where will the air go? The air as it is hitting it up. Now, meanwhile, more air will get heated by the ground, more air will be pushed up. So you have a continuous rising air column. So as the air column is continuously rising up, will it go hit the ceiling and again come down and again go and hit the ceiling and come down like an oscillation? Or will it go hit that tropopause and then diverge? Once it hits the tropopause, that is when it will diverge overall. It will move in either directions. Okay. Now, as it moves in this direction, in the meanwhile, we have a colder region. A colder region means that you will have the ground which is cold. The air above it will also get colder slightly. Now, colder air means much greater number of particles, because what do we mean when we say cold? Anything which is cold, we can say that you have the extraction of heat energy from that. That is why a particular area is cold, because when you are putting in energy, it becomes hot. When you are taking out the energy, that is when it becomes cold. So when it becomes cold, that means the air is heavier, isn't it? Now that heavier air will sink. It will hit the ground here. Now, if this air has sunk here, the air above it will also sink. In order to fill the gap, the air above it will also sink. So the air above it will also start sinking in order to fill the gap. Meanwhile, this air which was moving here, it sees that vacancy, and meanwhile all this air is on the region of tropopause. Now at the region of tropopause, that is the top of troposphere, the temperature will be high or the temperature will be low? What do you think? At the top of tropopause, the temperature will be very high or the temperature will be very low? Why is it that it will be very high? I have the best answer. Not taking any of them and taking the answer as moderate. No. I'm talking about the top of troposphere. Why is it at the top of troposphere you say that the temperature will be very high? Any of us? Only hot air will be there. Is it that the previous portions which have been covered are regularly forgotten very easily? Just previous class we have covered ozone. Ozone is present in troposphere. How many of us feel that ozone layer is present in troposphere? Avni, Ananya, Neha, Shiva, Kavita, Muni. Ionosphere is present in troposphere. Okay, how many of us have not taken a look at what has been taught in the previous class? It appears as if many of us are coming here for the first time. Then there is no point taking so much time in discussion of the topics. We can simply skip ahead. Okay, so I'll not ask you questions, I'll tell you the answer here. Basically, the top of troposphere will have very low temperature. The temperature range at the top of troposphere is somewhere around minus 60 to minus 80 degrees Celsius, because in the region of troposphere we have a positive lapse rate. So here we have a positive lapse rate. So at the top of troposphere we have a very very low temperature. Right. So at the top of troposphere, we have a temperature close to around minus in the range of minus 60 to minus 80 degrees Celsius. And in case all those attentive candidates, with this particular approach, geography is something which you will never be able to cover. Let me provide that assurance to all of you. All those who are having that kind of an approach that what is done in the class will revise sometime later, let me tell you, geography is something you will never understand by that. So here, the temperature graph that you saw at the top of troposphere, it is around minus 60 degrees Celsius. It gets warmer in the region of stratosphere, and at the top of stratosphere, you have around 0 degrees Celsius. So that is why when we talk about the top of tropopause or the top of troposphere, the temperature is very, very low. So this air also becomes very cold. Okay, this becomes very cold. So as this becomes very cold, then what will happen? It becomes heavier, and wherever it sees a vacancy or a gap, it will start sinking. Already this is a colder region, so that has provided that kind of a gap. Now in this portion, when we have considered a hotter area, because the air is consistently rising, so in this portion we can say that a vacancy has been created because the air which was present there, that has risen up. And here we can say that there is a surplus which has been created because of sinking air. So because of rising air, we have a vacancy. Because of rising air, a vacancy is created. And here, because of sinking air, you have a surplus of air. So always, if in one region you have a surplus of gaseous molecules, in one region you have a deficiency, so there will be a general movement from surplus to the region of vacancy. And that is what we experience as the movement of air. And that is what is referred to as a wind. So always understand and remember that wind will blow from a high pressure to a low pressure. That high pressure and low pressure can be created by different circumstances, but that is where in the region of the high pressure, this is the region of the high pressure, where you have the sinking air because of cold conditions. Here you have the condition of the low pressure because you have rising air because of heating. So from the high pressure to the low pressure, there will be a movement of the wind. So always winds will blow from a region of high pressure to a region of low pressure. Always. Okay. So that is a basic fundamental that you have to keep in mind, because in high pressure you have a sinking air, means surplus amount of air molecules. In the case of low pressure you will always have a rising air, so you have a deficiency of air molecules, so that will be fulfilled, and that is how you have the wind movement. So this is basically the root cause of wind movement that we encounter on a day-to-day basis. But as I told you, that pressure is not always going to be determined by only temperature. Pressure is basically determined by many other factors, temperature being just one of them. So there are other conditions based upon which the pressure will vary. So here we introduce ourselves to that particular concept. So that is why you have the concept of thermal and dynamic pressure zones. So when we say a thermal pressure zone basically indicates those conditions of low and high pressure which are initiated by the conditions of temperature. So low and high pressure conditions created due to temperature. Whereas when we talk about the dynamic pressure zones, here the low and high pressure conditions shall be created because of movement of air. That is why the name dynamic. Low and high pressure is created due to the movement of air. Now, here, when we talk about the thermal conditions and the dynamic conditions, first of all, talking about the thermal conditions, which we have already talked about. So, any region which gets heated up, that will heat up the air above it. So, the air density will get lower. That means the air will get lighter and it will rise up, creating low pressure. Any air parcel which gets cooled down means more particles will be contained in that air sample or air parcel, and that will increase the air density, it will increase the weight, it will sink down, creating a condition of high pressure. So due to heating, we have air density decreases, air becomes lighter, rises up, creates low pressure. So that is where heating will always in certain conditions create low pressure. Whereas when we talk about cooling, so in the case of cooling, air density increases, air becomes colder or air becomes heavier, sinks, and you have high pressure. So this is the condition of the thermal high and low pressure which is created due to the conditions of heating and cooling. So wherever the region is heated, there can exist a condition of low pressure. Wherever the region is cooled, that can create a condition of high pressure. Now, when we talk about the region of a dynamic pressure zone, here the pressure movements are created due to the or the pressure conditions are created due to the movement of air. So if we consider any particular region, for example, here we take the case with the help of a room example. So here, if we have the air which moves, let's suppose, if the air is, let's say, you think about any closed room, any room that you are sitting in. Now, that room will have the ceiling, the roof, the floor as well. So, if let's suppose you have large fans which have been installed in the floor, near the floor, large, very large fans from both sides, and they are continuously blowing air near the ground surface. Now, this air, when it is coming, confronting each other, what will happen? This air has got no other place to go. It is attacking each other. This air is basically moving here towards each other. So in this case, the air has got no other place to go, but as the air collides and converges, it will have to be rising up. The air will have no other place to go but rises up. It hits the ceiling and diverges again. Right? So here, when you have the rising air at this particular portion, you have rising air. Rising air, we have seen, is always associated with low pressure condition. So that means whenever you have convergence of air on the ground surface, it will create a condition of low pressure. Convergence of air on the ground creates rising air. And that rising air is basically going to create a kind of a low pressure. Now, when we talk about another condition where we reverse this. So if we have air which is moving at the roof, if we have, let's say, exhaust fans at the region of the roof here, or rather cooling fans which are installed here. Now, as the air moves here across the roof in this area, now as it collides with each other, it will have no other place to go but then to sink down. So this air will have no other place to go than to sink down. It is being forced down here. It does not readily want to come here, but because the air has got no other place to go, because it is converging from both sides on the top, so that is why it sinks down. And as it sinks down, that is when it will start to diverge. So on the ground surface, here it will end up creating a condition of sinking air. And sinking air is associated with high pressure. So convergence of air in the upper region pushes the air down, causing divergence at the surface. This creates a condition of sinking air, and that is associated with a condition of high pressure. So we have seen that basically a low pressure or a high pressure condition can be initiated both by temperature as well as the movement of air. When we talk about the role of temperature, any region when it gets heated up, it will heat up the air above it as well, and that heated air will tend to become lighter, it will rise up. Any region which is cooled down, the air above it also cools down. It gains a greater density because more number of particles will be included in that air parcel. It becomes heavier and it tends to sink. That is why heating creates a rising air column, cooling creates a sinking air column associated with low pressure and high pressure respectively. When we talk about the creation of a dynamic pressure zone, this is independent of temperature. These pressure zones are independent of temperature. So in this case, if you have winds which are blowing on the surface and they converge together, they have no other place to go but then to be pushed upwards. So as they are pushed upwards on the ground surface, if the winds are pushed upwards, it will create a condition of low pressure on the ground surface. And that is what is referred to as the convergence creating that low pressure. But if there is winds moving in the region of the top of the troposphere is the region closest to the ground surface. That is the layer of atmosphere where, as you move higher up, you have a positive lapse rate and it gets colder. So, at the region of the top of the troposphere, which is referred to as the tropopause, beneath the tropopause, if you have a movement of air towards each other, now that air will converge with each other. And as it converges, it has got no other place to go, but it will be forced downwards. As it sinks downwards, it will be hitting the ground surface. Regardless of the temperature of the ground surface, as it hits the ground, it will impose its weight. It will end up creating a condition of high pressure. So these conditions of low and high pressure, they can be created either by temperature or can be created by the movement of the wind. When they are created purely by the movement of the wind, we refer to them as the dynamic pressure zones. When they are created purely by the aspect of temperature, we refer to it as a thermal pressure zone. Now we talk about the portion of isobars. Just like isotherms, we end up representing the pressure changes and the distribution of pressure in various different areas by what is referred to as an isobar. Isobar here represents an imaginary line which ends up joining those places indicating the similar pressure. Because when we talk about isobar, iso here stands for similar or same, and bar here represents the condition of pressure. So isobars will end up representing places of various different pressure. Just like what we saw in the case of isotherms, here also in the case of isobars, we can never have a condition where two isobars can crisscross each other. So no two isobars will ever crisscross each other. Isobars can ever crisscross each other. Why? Because when we talk about an isobar, so isobar, any place lying on an isobar represents a particular unique pressure. And if you have an isobar crisscrossing each other, that means in those conditions, a particular place will have to indicate two pressure conditions at the same time, which is simply impossible. So hence, they can never crisscross each other. Now, here it is a line on the map connecting points having same atmospheric pressure at a given time or an average over a given period. Now, these isobars, they also help us understand about the change or the variation in pressure as you move over a particular distance. So, the placement of the isobars help us understand the variation of pressure over a particular distance. So in this case, for example, let's suppose we consider two particular conditions or two particular regions. Each of these isobars, they end up representing a very unique kind of pressure. If we take the case of the map of India here, you will observe each of these isobars, they represent a unique pressure. For example, here you will observe it is written 996, 997, 998. So any point which is lying on this isobar will experience a pressure of 996 millibar. Any point lying on this isobar will experience a pressure of 997 millibar, and that represents a variation in terms of pressure. So when we express this, let's suppose we express this over a particular region A. Now in that region A, let's assume that we have the placement of isobars. Each isobar, let's say you have 1010 millibar, then you have 1009 millibar, then you have 1008, 1007, 1006. Let's suppose here you have 1000 millibar, and so on it continues. So here the isobars are present very, very close to each other. Let's assume here you have a condition of 980 millibar. And if you consider this to be a distance of 100 kilometer, it tells you that over a region of 100 kilometer, the pressure has varied from 1011 millibar, if I assume this, to around 980 millibar. So here, over a distance of 100 kilometers, pressure has varied from 1011, or basically has reduced by 31 millibar. That 31 millibar I have gained by subtracting 980 from 1011. That gives you 31. So over a distance of 100 kilometers, the pressure has reduced by 31 millibars. So if I take another such similar example, if I consider another particular region, if I consider another region as B here, again over a distance of 100 kilometers, if I have the isobars in this case, which are spaced apart from each other, which have a significant amount of distance between each other. If this represents 1011, this represents 1010, this represents 1009, 1008, 1007, 1006. So in this case, over a distance of 100 kilometers, pressure has reduced by 5 millibar. So over the same distance in both these cases, we have seen that the pressure changes in a different manner. And that can be depicted by the placement of the isobar. So we can have a conclusion that if the isobars are placed very close to each other, that means the pressure is changing very rapidly. If the isobars are far away from each other, that indicates a condition that the pressure is changing very gradually. So This is what represents the placement of the isobars and depiction of the variation in pressure. Hence, if the isobars are placed very close to each other, it indicates a greater difference in pressure. If the isobars are placed far away from each other, it indicates a gradual variation in pressure. So, by the placement of the isobars, we can always come at a conclusion whether the pressure is changing suddenly or whether the pressure is changing very, very gradually. If the isobars they are very, very close to each other, that means suddenly in a short span of time or in a short distance, the pressure is changing. If the isobars are placed very far away from each other, that means you have to go for a long distance and then the pressure starts to change. Now, this variation in pressure over a particular distance, that is what is also referred to as the pressure gradient or the change in pressure. So, as the pressure changes over a particular distance, that is what is a pressure gradient. So, for example, when we take a look at this map, if you consider this particular distance, you'll find that there is a variation in pressure from what can be expressed as around 999 millibar or 998 millibar to around 1010 millibar. So here over this distance, the pressure is changing from 999 to around 1009. So that variation in pressure over a distance, that is what is referred to as a pressure gradient. So when we talk about pressure gradient of any particular region, it always indicates the change in pressure with horizontal distance. So how is it that the pressure is changing over a particular distance? So it can change very significantly, very acutely. It can also end up changing very, very gradually and very slowly as well. So here always you will have the condition of pressure gradient is an important factor in contributing to the wind direction, something that we'll see later on. So pressure gradient is something which can be understood with the placement of isobars. So if the pressure gradient is high, or if rather, if the isobars are closely spaced means pressure is changing rapidly, which means we have pressure gradient is high. That is because pressure gradient is indicated as the change in pressure. So if the isobars are closely spaced with each other, that means the pressure is changing quite rapidly. That means the pressure gradient is high. If the isobars are distant from each other, that means pressure is changing very slowly, that means pressure gradient is very low. Now, this pressure gradient is an important factor in order to determine the direction, or rather, in order to determine the wind which moves from one region to another. We have seen earlier that wind will always end up moving from a region of a high pressure to a region of a low pressure. Always the wind will be moving from a region of high pressure to a region of low pressure. Under no condition will you come across a circumstance where a wind will blow from a low pressure to high pressure. So, wind always blows from a high to a low. Now, when we say that in a particular region the pressure gradient is there, means one region will be there where the pressure is high, one region will be there where the pressure is low. So if you take the look at this particular analogy, is this if this particular schematic, if you take a look into, so that means pressure gradient means what? That in one region the pressure is high, in one region the pressure is comparatively low. So that is what is referred to as the pressure gradient, that the pressure varies over a particular distance. This indicates the variation of pressure over a particular distance. Of pressure over a distance. So always you will have, when we say a variation, means one region will have a high pressure, one region will have a distinctly low pressure. So when we talk about a region of high pressure, so in the region of high pressure, you will always come across a surplus of air molecules, whether it is caused by the sinking of air or whether it is caused by cooling of air. Region of high pressure will always end up having a surplus of molecules. Region of low pressure will always end up experiencing a deficiency in terms of the molecules. So that is where you will always end up having a kind of a movement from the region of high pressure to the low pressure. And that is what we encounter as the wind. So in a way, we can say for the wind to exist, any kind of wind to exist, you need the presence of a high pressure, you need the presence of a low pressure, because the wind will always move from a region of a high pressure to a region of a low pressure. That difference between high pressure and low pressure, that is referred to as a pressure gradient. So in a way, we can also say that higher the condition of a high pressure, lower the condition of a low pressure, the gradient will be much more significant. So if the difference between high and low pressure is very high, the gradient is very large. If the difference between them is smaller, that means the gradient is less. So greater the amount of pressure gradient, more particles will end up moving towards the low pressure, and hence stronger will be the wind motion. Lesser the pressure gradient, less pressure gradient means the difference in pressure. So lesser the pressure gradient means lesser particles will be moving towards the low pressure, hence weaker will be the wind. So this particular kind of wind movement which is initiated because of the difference in pressure, that is what is referred to as the pressure gradient force. And that pressure gradient force is responsible for initiating the wind motion. So here when we talk about it, so we can always conclude here by saying that greater, or if the difference between high pressure and low pressure is greater, means pressure gradient is high. If the pressure gradient is high, means more particles will be initiated in the wind motion. So pressure gradient, or rather wind movement, is directly proportional to pressure gradient. wind movement is always going to be proportional to the pressure gradient. So if the pressure gradient is high, the wind movement will also be higher. If the pressure gradient or the difference in pressure is low, the wind movement will also be significantly slower. Now, after this, we come to the factors which end up influencing the velocity and the direction that the wind ends up taking in any particular region for any particular area. So when we talk about the wind in general, also as it is experienced, and that is a common occurrence, that the wind which is experienced is not always going to be coming from the same direction. The wind that is experienced in different seasons, that wind also will never have the same velocity. So the wind velocity, the wind direction, it keeps on changing quite frequently. So wind, in fact, is dependent on three major factors, and that is the pressure gradient force, the Coriolis force, and the frictional force. What they are, we'll take a look into it. But when we talk about these winds, gravitational force is also a significant portion which keeps the wind sticking to the ground surface. So gravitational force is one of the key components which keeps the wind stuck to the ground level. Other than that, you have three important forces which contribute to the direction and the velocity of the wind, and that is the pressure gradient force, the frictional force, and the Coriolis force. So when we talk about each one of them, starting with the pressure gradient force. What is a pressure gradient force? That is a kind of a force which is primarily responsible for the initiation of the wind movement in itself. No wind can come into existence without the existence of a significant pressure gradient force. So when we say a pressure gradient force is present, that will always be acted whenever you have a gradient of pressure, whenever you have a difference in pressure. Just like in the case of water, whenever you have a height, whenever you have a height difference, there the water will always flow from a higher level to a lower level. Never would you have encountered the water to be flowing from a lower level to higher level. So water will always use the height gradient. Similarly, when we talk about the wind will use the movement of the air particles. So the air particles will always be moving from a region of a surplus to a region of a deficit. A region of a surplus is indicated by a high pressure. A region of deficit is indicated by a low pressure. And that difference between high and low pressure is referred to as a pressure gradient. So greater the pressure gradient, greater will be the movement of particles, and hence stronger will be the wind movement. Lesser the pressure gradient, lesser will be the movement of particles, and weaker will be the wind. So the rate of change of pressure with respect to distance, that is what is referred to as pressure gradient, which in a way ends up indicating the difference, indicates the difference between high pressure and low pressure. That difference between high pressure and low pressure over a particular distance can also be expressed with the help of the spacing of the isobars. Can be expressed by the spacing of the isobars. So if the isobars are closely placed, that means the change of pressure is very high. If the isobars are wide spaced or are distant from each other, that means the pressure gradient or the change of pressure is low. So that brings us to the earlier conclusion that we had drawn up above, that if the isobars are distant from each other, that means the pressure gradient is low. If the isobars are closely placed, that means the pressure gradient is always going to be high. And pressure gradient also ends up generating what is referred to as the pressure gradient force. So here, when we have isobars, when closely spaced, means pressure gradient is high, which means pressure gradient force will be high, which means wind velocity will be high. When we have a condition when isobars are far away, means pressure gradient is low. Pressure gradient is the difference between the high and the low pressure. That pressure gradient is low. That basically means the pressure gradient force which will be acting will also be significantly low. That basically ends up meaning that the wind velocity will also be significantly lower. So, in a way, with the help of understanding or taking a look and analyzing the isobars, we are always in a position to be able to tell whether the wind velocity will be faster or whether the wind velocity is going to be significantly slow. So, if we take a look at that with the help of a relevant example, this is the presentation of isobars over the region of North America. Now, if you take a look at the placement of the isobars, you will observe that this is a region of a high pressure, having a pressure of close to around 1036 and higher millibar. And this is a region of a distinct low pressure, having a distance or having a low pressure of close to around 988 millibar. But then the spacing of the isobars are not uniform throughout. In this area, you will observe that the spacing is very, very high. So that represents a shallow or a small pressure gradient. So that represents a significantly shallow pressure gradient. Whenever you have a shallow pressure gradient, that will be associated with a weaker wind movement. And then when the isobars are closely spaced, in that condition, that means in a very short distance, the pressure is changing drastically. In a small distance, the pressure can be changing quite drastically. So that means the difference in pressure or the pressure gradient is going to be very, very high, and that will always end up initiating the strong wind movement. So the wind movement is primarily to be determined with the pressure gradient force. So we can also say that wind movement or wind velocity is directly proportional to the pressure gradient force. If the pressure gradient force is high, the wind velocity will also be higher, and vice versa will also end up coming true. So that is basically the aspect of pressure gradient force. Then we have Coriolis force and frictional force. That is something we'll take a look on Monday. So that will be all from my side here today. So we'll take a couple of questions and then we'll end the session here. And then we'll continue this portion on Monday. Cyclone formation can happen in either the thermal or the dynamic pressure zone in either of the cases. Why can't we feel the atmospheric pressure? Because our body is utilized or used to this particular pressure. That is why when you fly up in the airplanes, you require a particular pressurized cabin. If the airplane does not maintain that pressurized cabin, that is when people start bleeding out of their nose because the outside pressure is very less. That is why when people go higher up into the space, they require space suits because our body is something which is habituated to extremely high pressure. That is why whenever you go for mountaineering, you feel dizzy and you require certain amount of acclimatization in order to get used to the low pressure on top of that mountain. So if tomorrow, let's suppose you decide to go to the Siachen Glacier, first of all, you cannot. But secondly, your body will not allow you to do so. You will basically end up dying if somehow today and tonight someone drops you on top of Siachen Glacier. Maybe you will die within next 12 hours. That is because the body is not used to it. So that is where you need acclimatization to handle that low pressure condition. And isotherms are basically the imaginary lines which end up joining places indicating similar amount of pressure, similar amount of temperature. Difference between a common current and an ocean current. What is a common current that you are referring to? Winds will travel horizontally and vertically as well. Recently, temperature is found to be warmer in Darjeeling than Kolkata. Temperature inversion, but is acting. Not always so. So there, the region of Kolkata has been experiencing lower temperature because of other variety of conditions, including excessive amount of rainfall, whereas the region of Darjeeling has been deprived of rainfall for significant amount of time and higher insolation with altitude that has raised the temperature. Yes, any of you who don't have a question, you are free to leave the class. Ocean current is always on the surface of ocean. Yes. How soldiers work in Siachen? They go through multiple different phases of acclimatization. No, today we won't have map pointings. Both processes are using fan, then why don't the pressure is not the same? That is because in one of the case, if you recall, the fans were blowing air at the bottom. In other case, the fans were blowing air at the top. So when you blow air at the bottom, the air will collide and will rise up. When you blow air at the top, it will collide and sink down. About the PYQs of geomorphology, I would rather suggest to you to get an idea, take a look at those questions. Any doubts that you have, frame a question on that. Otherwise, we'll take it up for discussion on next week. Adiabatic is basically the change in temperature which is observed in the air parcel purely because of the change in volume and not because of any additional or external source of heat. If the surrounding has low pressure, it means the temperature is high. Not always. It can also have a kind of a low, low temperature or a high temperature. It can also have a dynamic pressure. We experience low pressure in the mountainous regions because the air gets less dense as we start going higher up. The air is going to be of maximum density closest to the surface or at the sea level. And as we start moving higher up, the air density keeps on reducing. Planes would operate quite normally in the case of temperature inversion because the planes do not require colder or warmer air to move. They just require the air density in order to operate and in order to provide them with a kind of an uplift. In Andaman, which one is observed? What kind is the question is not clear. 50% of marks is attained in the subjective questions. Pressure belts is something that we are going to study in the next class. As the temperature in troposphere is lower, then why does the warm air get diverged instead of becoming colder? Because troposphere, cooler temperature, it should start to sink again. So as it will sink again, but here, if you have to think about it and if you can imagine, the air parcel is consistently rising up. It is not as if one air column has gotten heated up, it will rise and that is the end of it. Because once you have the region which is getting heated up, it will continue to heat the air parcel. So it will rise up. Other air which will replace it will also rise up. So that continues to push it to the tropopause. As it hits the tropopause, there is a continuous stream of air coming from underneath it, and that is where the air has got no other place but to diverge in the region of tropopause. The placement or the ice impact of global warming on the placement of isobars, there is no significant impact in the sense that isobars themselves are something which is variable on temperature. So isobars will keep on changing multiple times during the day. It will keep on changing multiple times during the month and during the years as well. It is an average of these isobars that we consider for any kind of distribution of pressure. In Andaman, which pressure gradient force? Kindly revise the portion of pressure gradient force, Vivek, again with the help of the recordings of the videos which are available. Pressure gradient force is basically the difference in pressure which exists. It is not that Bihar will have a separate pressure gradient force, Jharkhand will have a separate pressure gradient force, Chhattisgarh will have a different pressure gradient force. That is not how it works. Wherever you have a high pressure, wherever you have a low pressure, the difference between them, that is what is referred to as a pressure gradient force. The class that we are covering, does it cover more than 70% of portion, mains portion as syllabus? This class, the live class, if you are attentive, And if you are revising enough, which many of you obviously are not, if you are revising significantly, this will cover 100% of your main syllabus, along with the portion of current affairs is something that you have to follow. Last year also, year before that also, out of the 105 marks of the questions which were asked, close to around 85 to 90 marks were directly taken from the PPTs. And along, obviously, you needed to have input from the portion of current affairs. But you have to understand one difference. From the same class, you have candidates who have secured a good rank within double digits. And from the same class, you have candidates who have been repeating this ever since again. So, which side you want to lie on, that is something which is up to you. So that is where we'll end the session here. Any doubts that further prevails, you will have the SMEs which will give the answer, or you can write to us by mail as well. So till we meet again, take care of yourself. Goodbye. Thank you.